The boys turn.
Okay. Today is, what is today? Wednesday. Last time we did hypothesis testing for proportions. So today we're going to do the same thing, only, what? Yeah, today's means. Hypothesis testing for means. Okay? So it really is the same thing. It's just the test statistic is computed a little bit different, and you look up the p-value from a t distribution instead of a z distribution. For you, mostly that means instead of going to one prop z test, I'm going to go to the t test, a different place on the calculator. Okay? So, we'll jump right into it. Remember last time I had 5 steps for hypothesis testing. What was the first step for hypothesis testing? Check the assumptions. Okay? So for means problems, hypothesis test for means from one sample. And by the way, chapter 9, everything in chapter 9 is one sample problems. When we get to chapter 10, it's 2 sample problems. So you're gonna, as we go through the rest of the semester, you're gonna have to keep adding to your repertoire of things that you can do. And you have to ask yourself, first thing you ask yourself is this a proportions problem or a means problem? Then once you decide that, is this 1 sample or is it 2 sample? And so on. We'll get more and more of those kind of questions. Right now, we've only done 1 sample, means and proportions. So that, if we're doing a means problem, first we have to define what are our assumptions. So what's the first assumption that has to be met?
Random sample.
Random sample. And it's always the first assumption. So random sample. Okay, second assumption.
15 successes.
Okay.
Sample size greater than 30.
Yeah, what you said, Jory, was for proportions, right? 15 successes, 15 failures. That's for proportions. Now that we're in means, it's not that, but it's at least 30. Or when can you get by with less than 30 if you're doing a means problem?
Smaller sample.
Yeah, if you have a smaller sample than 30, it's still okay if what? No, that's proportions. Remember the central limit theorem?
If you're less than 10% of the population. If you're
No, that's for proportions and not having independent samples. Okay, good try though.
Normal distribution.
Normal distribution, very good. So the second assumption is the data are normally distributed or if they're not normally distributed, n must be greater than or equal to 30. So one of those 2 things has to be met. If we're doing a hypothesis test about pulse, we can use samples of size 5 or samples of size 10 and not have to worry about it because pulse is normally distributed. But if we have something very skewed like our age distribution, then we better have at least 30 before we know that the sampling distribution of X bar is normal. Okay, so this is directly related to the central limit theorem. Okay, what is the second step to hypothesis testing?
Rank the hypothesis.
Write the hypotheses. So the null hypothesis and the alternative hypothesis. The null hypothesis always has what in it?
equal.
An equal sign. So it's always going to have an equal sign. The alternative never has an equal sign. It's got one of the other 3 signs, either a less than, a greater than, or a not equal. Now, what do we write for our symbol here? The mean, the population mean, which our symbol is mu. So this is mu equal some number. Now, as a placeholder for that number, we always use the same symbol and then a sub-zero. So this would be mu sub-zero. But that's always going to be a number that they'll give you in the problem. They'll say, test to see if the mean is 5. And you know you're going to stick a 5 right there. Okay? So then the alternative is mu either not equal to, or it could be a less than, or it could be a greater than, depending on the scenario of the problem. Right? And they'll tip you off as to whether it's one-tailed or two-tailed. They won't always come out and directly say it, but they'll give you a hint one way or the other. Okay, what's the third step?
Determine the correct procedure.
Determine the correct procedure. So if it's a one sample means problem, like this, what's it going to be? Well, means problems, we did confidence intervals for means already. Confidence intervals and hypothesis tests are very closely related. Do you remember where we went to do confidence intervals on a mean? We pushed stat, we went over to tests, and then down to what?
T.
What'd you say, Chelsea?
T interval.
T interval. So now we're going to do a hypothesis test. Guess where we're going to go? The calculator always replaces the int with test, right? So instead of going to T interval, we're going to go to T test. So for means problems, one sample means problems, we'll go to T test. The fourth step, to compute the test statistic and the p-value. Okay, the fifth step,
Are 3 and 4 the same in the book this time?
no, they do the same thing. In the book, he will say step number 3 is compute the test statistic,
Okay.
step number 4 is compute the p-value. So his 5 always stay the same, and my 5 always stay the same, but I changed the 3 a little bit because when we use the calculator, the test statistic and the p-value come out at the same time, so it's really you're doing the same thing, so why make 2 steps out of it? And the place where people lose points is that they don't know which procedure they're supposed to use, so they just take the nearest one. Oh, I remember talking about that one in class, and they hit one prop z test and go on, and that's not going to do it correctly for a means problem. What's the fifth step? Make conclusions. And we say the conclusion always must be worded how?
Whether you reject null or fail to reject null.
Okay, you say I reject the null or I fail to reject the null, but you can't stop there. What do you have to go on and do? Put it in the context of the problem. Right? So if we're talking about the average test score on the final, then your conclusion should say something about test scores of students on the final, not just reject the null. Okay? All right, so there's your 5 steps. I'm going to move that over here for us to refer to. And first thing I want to talk about is the test statistic. The test statistic is computed slightly differently than it was last time with proportions, but it's exactly the same concept, and it will always be this concept. Yeah, I guess I can say always. Not quite, but good enough for now. In proportions test, which we did on Monday, the test statistic told us the number of what? Remember we had an interpretation of that thing? Number of what? Number of standard errors that
P hat.
p hat was from the null. Right? The number of standard errors that p hat was from the null. Well, now we're doing means problems, so we don't have a p hat. What do we have instead of p hat?
mu.
No, that's the population mean, but what's the sample mean, the point estimate? X bar. So the test statistic is number of standard errors that X bar is from the null, which is mu sub 0. So how do I compute that? Well, we know it's going to be a t this time, not a z, because we use the letter t to remind us, well, we got to look up probabilities from the t distribution, not the z distribution. But we just take the distance x bar is from the hypothesized value, and then to put it in terms of number of standard errors, we divide by standard error. And what is the standard error of x bar? Go ahead. See? That's what I was testing to see. You started giving me the formula for the standard error for proportion. And remember, you get to have a cheat sheet, so make your cheat sheet, make sure that you have everything. I've even recommended you get both sides of a piece of paper. Make one side your means side and one side your proportion side. And make sure you get the formulas correct. You start mixing formulas and things, wheels come off real fast, right? So it isn't square root of p hat minus 1 p hat, no, and all that junk. It's something else.
Over the square root of n.
What's over the square root of n?
The
The standard deviation of population.
The standard deviation over the square root of n. Now we don't know the standard deviation of the population. If we did, we'd use it. But we don't, so what do we use instead? Well, think about it. I mean, use a little common sense. If I don't know the standard deviation of the population, what would I use to estimate it? The standard deviation in the sample, right? Remember, I've said this many times now this semester. Whenever you need to estimate something from the population, your best estimate is that thing from the sample. So if you need to estimate the population standard deviation, you use the standard deviation from the sample. And what's our symbol for that? It's not sigma, it's S. S sub x is the way the calculator does it, over the square root of n. And there's your standard error of x bar. So the test statistic gives us a number of standard errors, right? So suppose we do a hypothesis test, we compute the test statistic, and it comes up negative 3.4. By now, you ought to have a feel for whether that's a big number or a little number, or what do you think, Garrett? Negative 3.4. Would that be evidence against the null hypothesis, or evidence, or not strong evidence against the null hypothesis?
Pretty big for it.
Pretty big, and that's right. And why do you know that's pretty big?
Because that 99.7% is for 3.
Good. 99.7% of all x bars should be within 3 standard errors of mu 0, if mu 0 was correct. Right? So if the null was true, we'd expect our sample to be within 3 standard errors. And a negative 3.4 says, hey, you're more than that away. That would be pretty strong evidence that mu 0 isn't correct. Yeah?
Could that ever be evidence that your sample is just bad?
See, there's the rub. That's a great question. What she said was, could this ever be evidence that you just got a bad sample? And the truth is, yeah, it could be, but we never know which it is. We don't know whether that negative 3.4 is telling us you got a bad sample or that your null is wrong. So what we choose to do is say, well, we're going to decide that means the null is wrong, and accept that 5% of the time we might have made a mistake. We might have made the wrong decision. We might have just got a bad sample. So that's what that significance level is. That's the probability of just making a mistake by using our decision rule. And we have to live with some probability of mistake, so we keep it small, like 5%. Okay? So the p-value then is computed from the t-distribution, which is bell-shaped and symmetric, a lot like the normal distribution, but a little bit more spread out. Suppose I have my mu 0 right there, and if the null hypothesis is true, this will be centered at mu 0. And let's suppose I get an x bar that's right there. Where do I shade to get the p-value? Remember, p-value is a probability, and area under distributions gives you probabilities.
Your observation or further?
Your observation, x bar, or further from the null hypothesis. So there's my p-value. Now to really get particular here, is that a one-tailed or a two-tailed p-value? It's a one-tailed, because I only shaded one tail. If I was doing a two-tailed test, what would I also need to do?
Shade the other side.
Shade the other side symmetric to that. So that far away from here or further away in either direction. So I'd come down here and shade that same region. So two-tailed p-values are 2 times the one-tailed p-value. You just double it. Okay? But you don't have to worry so much about that other than just you need the understanding, because when you do it on your calculator, it's going to know. You're going to tell it, do a two-tailed test or do a one-tailed test, and it's going to automatically compute the p-value the right way. Okay? So that's all there is to it. Let's practice. Let's go to the homework set at the end of chapter or section 9.3. And I'm going to start with problem 936. And 936 is the problem about filling wine bottles. So let me dim the light. And pull this guy down. And there's problem 936. Can you guys read that okay? So here's the scenario. I'll read it, but I probably won't read every word. We've got what we have is we have a winery, right? And they're filling wine bottles. And they advertise, in other words, they write it on their label that the bottle contains 750 milliliters. Okay? Now, if you buy a bottle of wine, it says on there 750 milliliters net contents. Is that bottle going to have 750 milliliters in it?
No.
No. Exactly 750? No. There's no way to get it exactly, right? So it might be a little above it, it might be a little below it. Well, these packaging laws are dictated by the Food and Drug Administration, right? So if you want to advertise that it contains 750 milliliters, you need to make sure that most of the bottles will have at least 750 milliliters. You don't want to cheat people. If you set your machine to fill the bottle, and the amount in the bottle will be normally distributed. Most of the bottles will be real close to what the true mean is. And then the ones that are way high or way low will become less and less common, so you get this bell-shaped distribution. If you set this thing at 750, so that your machine on average will put 750 in there, what percentage of people will get too little wine in the bottle? 50%, half the people. That hacks people off. Right? You ever open a can of Pepsi or something and you notice, gosh, there's not much Pepsi in here. Well, you don't want it, you don't like that. People don't complain if you give them too much, but they do complain if you don't give them enough. So what would we want to do? We want to set our machine so that this distribution shifts from what's advertised. So let's say we set it at 752 so that 750 is down here. Then only a small percentage of people would be getting too little wine, and almost everybody would be getting too much, right? But you wouldn't want to shift it so far that now you're just wasting money, because you're giving them wine they're not paying for, right? So that's kind of the balancing act. So this is actually the kind of thing that gets done in food packaging, and they usually have a quality control department that does sampling to test to see that, yeah, we're doing what we say we're doing, and we have a high percentage of containers that have more than what's advertised. So this is kind of typical. 4 observations are taken each day to plot the daily mean over time in a control chart to check for irregularities. The most recent day's observations were 745, 740, 750, and 745. Now let's do the eyeball test. Without doing any fancy schmancy statistics, if you were the statistician at this company and they said, hey, here's our 4 bottles we sampled today, would you think the machine is doing what it's supposed to be doing? No. Every single one of the 4 is below the 752 that is their target. So there's a pretty good chance something's happened to the machine. It needs to be tweaked a little bit, right? Right below that it says, could the difference between the sample mean and the target value being 752, be due to random variation, or could you conclude that the true mean is now different than 752? In other words, it is possible that when they took a random sample of 4 bottles, they just happened to get the 4 with the lowest amount in it. That's possible, isn't it? But not very likely. Guess what the p-value tells you? How likely that is. Saying, well, yeah, it's possible, but if the p-value is 0.001, you're saying, well, there's only a 1 in 1,000 chance that this is due just to random chance. So then you would reject. Exactly. That's the way a hypothesis test works. So let's conduct it. It says, answer by showing the 5 steps of the significance test, making a decision using a 0.05 significance level. All right, here we go. What I'm going to do is I'm going to raise this up, and then I'm going to copy down that date over here so I can see it. 745, 740, 750, and another 745. Okay? Now, let's do the 5 steps of a hypothesis test. What's step number 1?
Assumption.
Assumptions. Now, I'm going to save a little bit of time by not writing out those assumptions again, but on an exam, I would want you to write them out and then tell whether they're met or not. The first one is random sample. So you're looking in the reading for it to tell you that these 4 bottles were chosen randomly. 4 observations are taken each day to plot a mean, blah, blah, blah. It never says they're randomly selected. So that assumption is it's not met. Actually, we don't know if it's met. We weren't given enough information. They didn't tell us how they selected the bottles. If they don't say it's random, then we have to assume it's not random. So we would say that assumption is not met. Second assumption. Data are normally distributed, or the sample is at least 30. Well, clearly it's not 30 because we only have 4 bottles. So we better have something in here that tells us that the data is normally distributed. Guess what? He didn't say that either. So neither of the assumptions are met, as far as we know. Now, the author does tell us that the t-test procedure, and he said this same thing when we did confidence intervals, that t-procedure is, quote, robust to this assumption, to the normality assumption. Remember what that means? it'll still work pretty well. Right? It'll still work, even though technically it's not completely valid, it isn't going to be off by very much, as long as there aren't any extreme outliers in your sample. And if I look at this sample, 745, 740, 750, 745, there's not one value that's way far away from the other values. So we're probably going to be fine. But on the test, you would say, I checked this assumption, can't tell. It doesn't say random. I checked this assumption, can't tell. It doesn't tell me the distribution that these bottles are. And there's no way you can do a histogram of 4 things and get an idea if it's bell-shaped or not. So you need a big sample to look at a data distribution.
Actually, that one is bell-shaped. Those 4 just happen to be.
Well, kind of. If you did a dot plot, it would look like this. Right? I guess that's sort of bell-shaped. Okay? So assumptions not met. So what do you do in practice if the assumptions aren't met? Well, if you're like most people, you never check the assumption. You just do it. And then you don't ever realize that, you know what, all my stated confidence and all that, they aren't valid. But in practice, if you do check the assumptions and they're not met, you either write a disclaimer and say, what follows is suspect, but I'm going to do it for exploratory reasons, or you use procedures that are called non-parametric, and that means they don't depend on parameters, they don't have these assumptions. But, and that's in the book, but it's beyond where we can get to in one semester. So I don't teach non-parametric, even though there are plenty of procedures that you could use if data is not normal or not random or whatever. Okay, so step number 2, write out the hypotheses. I want you to do this on your own paper, and then I'll do it up here and you can see if you got it right. Write out your null hypothesis. And then write out your alternative, and you'll have to read a sentence in here to figure out whether it's a less than symbol, a greater than symbol, or a not equal symbol. You got yours, Amy? Okay, your null is correct. Yep, that's correct. Good. Good. You're slow. Your null is correct. Good. I haven't seen anybody get it wrong yet. Except you, you're not really writing anything. What'd you write? Okay, all you gotta do is figure out, well, what value do I use right there? What do they say to test for? They say, test to see if the true mean is now different from 752. So that's telling you what? That mu is equal to 752 will be the null. The alternative, which symbol? Not equal. Because it just says is different than 752. And that is the scenario I would use if I was working at this company, because I would want to know either way. Am I putting too little in there? I'd want to know that. But I also want to know if I'm putting too much in there, because I don't want to be wasting money. Right? That's hurting profit. Okay, step number 3, determine the correct procedure. We already know this is going to be a t-test because that's the section of the book we're in. But if you were on the test, you wouldn't know what section I pulled that problem out of. So you'd have to realize, ooh, is this a means problem or a proportions problem? How do you know? Because it says means all over the place, right? The word mean is just in there all over, so it's got to be a means problem. It really is that simple to decide, but you'd be surprised how many people come in here and try to do a proportions test on this thing. Make that decision. You have to, it's just a matter of thinking about it, taking the time. Okay, so now let's do step number 4, which is the test statistic and the p-value. And we're not going to do those by hand, we're going to do them using our calculator. So, where do we go on our calculator? says to go to t-test. So you're going to push the stat button. Then you're going to go over to test. And you're going to go down to t-test, which is only the second one down, so it's easy to get to this time. And press enter. Now it says data or stats. Which is it?
Data.
Stats, what is it, the data, you could do data.
Well, what did they give us? Did they give us summary statistics from some sample, or did they give us the values of that sample?
Values.
The values. They gave us the data. So we need to tell our calculator the data, but as soon as you do that, it wants to know, okay, what list is your data in? Well, I haven't put my data in a list. So I've got to back out of here, go put the data in a list, and then come back into here. Okay? So, push the stat button, go to edit this time, and enter the data into L1. You don't have to go in L1, you can go in any list you want, but just remember what list you put it in. Okay? As soon as I hear no more buttons clicking, then we'll go on. Everybody got them in? All right, now we can go back to t-test, stat button, test, down to t-test, press enter. Press enter while the data word is blinking, and that selects it. And then the next thing down is mu0. What value do I put in there for mu0? 752. Okay? The value from your null hypothesis. A really common mistake is to put in the sample mean there instead of the hypothesized mean. If you do that, you'll get really bizarre results. So put in 752. Tell it that your data is in L1 if that's where you put it. The next line says FREQ, freak, that's short for frequency, and that's what you would use if you had, like in a frequency table. You say, well, these values the values are in L1, comma L2, but we're not going to do any like that, so just always leave that as a 1. The next line is you're picking what your alternative is. So mu is not equal to mu0, or mu is less than mu0, or greater than. And so you just match what you wrote in your alternative hypothesis. So we use the not equal symbol, pick the not equal symbol, and go down to calculate. So it tells me that in step number 4, so I'll move over here to where it's clear. Step number 4, the t-test statistic is negative 3.43 if I round to 2 places. And that's why I used that number negative 3.4 earlier, because that one was stuck in my head from my earlier class. So we've already decided, hey, that's a big value. That's out there in the tail. That's evidence against the null. The p-value tells us how strong that evidence is. So it's 0.0416 if I round to 4 decimal places on the p-value. Okay? So what's step number 5? Draw your conclusions in the context of the problem. So you better be talking about wine bottles and milliliters of fill, right? So what is the conclusion? First decide, do I reject the null or do I fail to reject the null? And how do you make that decision? What did you say? Did you say you were gonna?
No.
Well, I'll ask you anyway. How do you decide?
I don't know.
Yeah, you do. Remember, if the p-value is small, then it's evidence against the null, right? So how small is small? What do I compare it to?
The t value?
No, not the t-value. the alpha level, the significance level, which I forgot to ever write down, but what is the significance level? The last sentence of the problem said, use a 0.05 level of significance. Now, both the book and me, sometimes when I write out one of these problems, I'll forget to say what alpha level to use. So if it doesn't say, use 0.05. Right? And a lot of times it won't say. So this is less than 0.05. So what's my decision rule? Reject the null hypothesis. So this is strong evidence that the null is false, which means I have sufficient evidence to claim that the alternative is true. So that's the way I want you to write your conclusion. We have sufficient evidence to conclude the mean quantity of wine is different than 752 milliliters. Now, why was I careful to use that word different than? Because that's what I was asked to test. See if it differs from 752. Would I have been okay to say is less than 752? Because it was in fact less than 752. And the answer is yeah, you're justified in saying that. Even though you did a two-tailed test, you know which side of the null your data fell, it's okay to use that word. Not only do I know that it's different, I know that it's less than. Okay. So either word is okay. So that's what I mean when I say write the conclusion in the context of the problem. Don't just write, I reject the null, and go on to the next problem. You have to talk about the scenario of the problem. Okay? Now, just for fun, I want to put a confidence interval for the true milliliters, the true mean number of milliliters of wine that is being put in these bottles. Before I do that, will that confidence interval, just take a guess, will that confidence interval contain 752? Will it capture 752, or will it miss? It should capture it? And you say, no, it shouldn't. It should capture the true mean, but what did we just say about 752? It's not the true mean, right? We just said, hey, we don't think it's 752. So we say the confidence interval is probably not going to contain 752. So let's do it. Instead of going to t-test on your calculator, go to t-interval. And it should already be set up the correct way. The t-interval is the 8th one down. So again, select data. Tell it your data's in L1, and go down, set the confidence level, and hit calculate. So the confidence interval is 738.5 to 751.5. Does it contain the null hypothesis? No. So you can do hypothesis tests using confidence intervals. If the confidence interval excludes the null hypothesis, then you reject the null hypothesis. If it includes the null hypothesis, then you fail to reject the null hypothesis. Right? And that makes sense. Remember what a confidence interval is. It's the set of all values that you think are plausible values for the true mean. And since 752 is not in this interval, I'm saying I don't think 752 is plausible. I don't think there's any way it's 752. Does this allow me to say the null is true? I accept the null hypothesis. Can you say that? You can never say that. All you can say is, I fail to reject it, because of the confidence interval interpretation. Suppose this interval was 753.5 for an upper bound, so that 752 was in there. Does that allow me to say the mean is 752? No. It says it might be 752. 752 is plausible. But so is 740. So is 741. So is 753. There's lots of numbers that are plausible. 752 is just one of them. So you could only say, I fail to reject it. Excuse me. Notice that when you accept the alternative, you aren't pinning it down to a single number, which makes it, that's why you can say that. You can never say that you're sure it's a single number, because all you can do is a range of numbers. Okay? Now I want you to work problem 932, which starts out about young workers. So there it is if you don't have your book. You can't quite see the last line there, but it says, state the conclusion in context. When 197 workers aged 18 to 25 were asked how many hours they worked in the previous week, the mean was 37.8 with a standard deviation of 13.3. Does this suggest that the population mean work week for this age group differs from 40 hours? So answer by, and he's leading you through the steps of the hypothesis test. It never asks you to check assumptions. So let's do that real quick. Is the data random? It doesn't really say, but it says it's from the GSS, which stands for General Social Survey, which is an actual nationwide random survey that's done every year by the U.S. Census Bureau. So it is a random sample. What about normality? Does it say the day is normally distributed? No, but is it still okay? Because the sample size is larger than 30. It's 197, so we don't have to worry about normal. Right? So first assumption, or the assumptions are met. Okay, now go ahead and do part A. I'll go ahead and do that one with you. Identify the relevant variable and parameter. What's the relevant variable? The sample mean number of hours. What's the relevant parameter? The population mean number of hours worked in a week, which we'll label as mu. Okay? So then, if B says state the null and alternative hypothesis, find and interpret the test statistic, find and interpret the p-value, then make your conclusion. So you do that, and then we'll see how you do. And I'll talk to the camera. Those of you watching on video, pull out your books and do this problem, and then I'll turn the camera back on when we're done. Okay, so this should be your null and alternative hypothesis, that the population mean is 40 versus it's not 40, because that's what they say to test. Does this suggest the population mean work week for this age group differs from 40 hours? So that's what you're testing. Is it different than 40? Okay? if you put the sample mean right there, 37.8, then that's always going to lead you to strange results, like getting a p-value of 1. All right, so then what is your test statistic? This is step number 4,
Negative 2.3217.
3217. Okay, now that's kind of a medium-sized t. It's going to be kind of borderline. What's the p-value?
0.0213.
0.0213? Oh, yeah, I guess the last one we had was like negative 3 point something, and the p-value was only 0.04. Well, now it's not as far out in the tail, but the p-value is much smaller. But why is that? Sample size is so much bigger. Last time we only had 4 bottles of wine. Now we got 170 or 197 workers. So the distribution is much tighter. So 2 is further out there. Okay, so what's the conclusion?
I have sufficient
Are we
evidence.
using 0.05?
That's a good question. Are we using 0.05? It never says, does it? So when in doubt, use 0.05. So this is less than 0.05. So we're going to reject the null, which means our conclusion, we have sufficient evidence. Sufficient evidence to conclude what?
The true population means differ from 40 hours a week.
Conclude that the true population average work week now this is a population of 18 to 25-year-olds. Remember they specified what the population was. Average work week is, you could say is different than 40, or you could actually say it's less than 40 because that's where it turned out to be. Is less than 40. The only thing that you would change in this sentence, if the p-value had been bigger than 0.05, the only thing you would change is you would say, you put a little do not have in front of there. We do not have sufficient evidence. Okay? It's the only thing that you change. So you either say we do have sufficient evidence or we do not have sufficient evidence. And then you always talk about the alternative hypothesis. Always address the alternative in your conclusion. Isn't this fun? All right, we'll see you on Friday. And homework due tonight over 9.2. Friday is 9.3.